Is it? Can you use the number, the other one? Yeah.
Okay, next we'll have Piotr tell us scattering from production in 4D.
Okay, thank you. So first, I'd like to thank the organizers for putting together this amazing workshop in this great place. Thanks, guys. Yeah, I'll be talking about something more connected to Utin's talk yesterday than really directly celestial things, although I would hope that at some point the celestial program can really meet the S-matrix bootstrap program and give some insights in there. So I'll be talking about some work in collaboration with Alexander Zhiboyedov, and mostly some paper to appear. That's a follow-up from our paper last year, which is going to be about, and this is going to be about constructing S matrices which satisfy all the axioms that we know. So I'll start with some introduction, where it gives some motivations and kind of repeat a tiny bit of what Utin said yesterday. So I'll describe briefly the notion of non-perturbative unitarity that we want to be solving, and then this program of scattering from production, which is the trick that allows you to actually solve these S matrices. And then I'll present some results if there is enough time. Okay, so we want to compute S matrices that satisfy all the axioms which we know, that are analyticity, crossing, and non-perturbative unitarity. There's going to be an extra. I'll be defining these notions more precisely as we go. And what we'll do is to construct S matrix functions. So we'll construct functions which satisfy these principles, and these functions, some of them are actual S matrices, and some of them are possibly, or maybe not, just functions which happen to satisfy the same axioms, but do not correspond to a theory. So the difficulty here is that, so for perturbative things, of course, we have Amplitudes methods that work amazingly well. We can compute things extremely efficiently to very high orders and so on. But as soon as you want to do things non-perturbatively, given crossing, it's really hard to come up with ansatz that solve unitarity, and indeed there's no function today that does the job. In 2 dimensions, because of integrable models, we have many examples of functions which satisfy all the axioms. But in higher dimensions, we have no examples. And this whole prospect was revived by the CFT bootstrap, by the revival of the CFT bootstrap, which triggered the hope that maybe we can also revisit the S-matrix questions with numerics, with the power of modern computers. So thing is that computing the full S-matrix, which means all the end-to-end processes, is too hard a task maybe. So we'll restrict to the 2-to-2 amplitudes, T, or S-matrices. And it's still non-trivial, of course, because all the 2-to-n processes enter as intermediate states in unitarity. So there's still some kind of, this would be the optical theorem. The imaginary part, discontinuity of the amplitude is equal to the sum over all the internal states. I singled out this guy because it's just the square of the left-hand side. It's just the 2-to-2, but the rest is 2-to-n. And the idea of this scattering from production trick is to reverse the sign, the equal sign, to put this guy on the left-hand side, and to treat this thing as an input. So we will not. This is the thing we'll try to solve, and this is the thing we'll plug in as a function. And by spanning the space of all such functions, we know that some of them are correct S-matrices in there, and we can have a feeling of how big is the space of all these S-matrices, this exact S-matrices, and maybe we can identify some points, some special points, and then solve these special theories. So this is kind of what's written here. This trick bypasses the need to compute this multi-point, complicated multi-point processes. And by scanning all these inputs, we scan all the theories by definition. Probably we scan more, but at least all the theories, all the physical theories. And it's somehow a change of paradigm compared to the 60s, where people were trying to solve QCD. This is like trying to this is the bootstrap philosophy, just to span the space of all consistent functions and in objects. And in there, you try to locate the good ones, the interesting ones. And in this way, by realizing that the Ising model was at a kink in the space of allowed CFTs, you can, even though you don't really have a proof that it's supposed to be there, by applying further and further constraints, you shrink this kink to a small island, and then you shrink the size of the island and eventually you beat Monte Carlo for computing quantities of that CFT. So the hope is that maybe you could achieve similar things after you've been able to scan the space of theories. Of course, Yutin described, gave a very good state of the art for what's the situation in effective field theories yesterday, and people are still struggling to figure out if gravity or string theory is really at the kink somewhere, but this is all work in progress. So there's many existing approaches to attack this problem, and the gold standard is this PPTVRV paper, series of papers from 2016, 2017, which triggered a bunch of activity a burst of activity on this S-matrix numerical program. This plot here represents, for instance, the maximum cubic coupling of QFTs with a gap in 4 dimensions. And everything that's below these curves is a theory that's allowed. Everything that's above is not allowed. And so the way they got this plot is by applying fewer constraints than the amount of constraints which we know, and in particular the curves which lie at the boundary. I'll be more precise in a minute. The curves that lie at the boundary of these things, the S matrices that lie at the boundary of these curves, are in tension with a result due to Ax 64, Stanley Ax. It's only in 2 dimensions that you can have S matrices which are pure phases. In more dimensions, you cannot be a pure phase. You need to have production processes. And when doing their maximization, they find pure S matrices which look like pure phase. So there's a tension here, which is the thing we're trying to resolve with this program, because the full application of unitarity and some arguably strong version of analyticity, but well motivated, implies that you should not find pure phases. You should see inelasticity somewhere. Another thing is that they, with their ansatz, which actually Yutin described yesterday, which is kind of a polynomial ansatz, there's a particular structure, analytic structure, which you don't see, which emerges extremely slowly numerically. I'll describe this more precisely. It's this Landau curve business. So at the moment, there is no example of a function which seems to satisfy all these axioms. So the results which I'll describe are a numerical implementation of a program due to David Atkinson from a bunch of papers from the late 60s, early 70s. And so I'll show you by the end that we have some numerical implementation that seems to work, and that the axe that allows us to probe this axe or inelastic physics with a great detail of precision. There's still some things that we need to work out, but it's really promising. So yeah, any questions about this general introduction motivation part? Okay, so let me turn to sorry, say. Right. Yeah. Yeah. Exactly. Yeah. Or at least the method didn't allow to numerically know if there was production or not, because convergence is extremely slow. Okay. So as I said, we'll be looking at a gapped QFT, so no gravity yet, and we look at 2-to-2 scattering of scalar states and the lightest state. And we impose some kind of a Z2 symmetry to just have quartic coupling. It's a pion-like theory type of theory. It's a pion-like ensemble of theories. The goal is to construct these S matrices, and there's this notion of Mandelstam analyticity, which I'll come to in a sec. And yeah, the thing that's hard is this tension between crossing and unitarity, which is the subject of the next few slides. Oh no, it's just sorry. There's no particular reason to do this. It's just simpler. It's just it just looks like pion physics that have just the quark. We can yeah. It's including cubic terms is definitely doable, and it's on the to-do list. So when you don't have a cubic vertex, so your first threshold, normal threshold, corresponds to the two-particle cut. It starts at 4m squared. The next threshold is at 16m squared. It would be at 9m squared if you had a three-particle cut.
So what, like, how sensitive, or how hard would it be to generalize to without a gap?
Oh yeah, yeah. Very open question. If you have infrared divergences, probably you really need something else to deal with the very notion of unitarity. If you're in higher dimensions or have derivative interactions or anything that kills the infrared divergences, you might hope to still be able to run this scattering from production, but you won't have all these thresholds will accumulate here. So the cut starts here, and you, in particular, you don't have elastic unitarity, which is unitarity in the elastic strip. But the idea of inputting production to solve for some kind of scattering, it could still run. So let's hope. But more work. Okay, so there's kind of two notions of unitarity. I just want to skim partial wave unitarity because this is how you check. This is not how you solve. This is how you check that your end result is good or bad. So these guys fj's are partial waves coefficient at spin j. It's just some integral, some transform with orthogonal Gegenbauer polynomials in d dimensions, Legendre polynomial in 4 dimensions. And the sj's are the partial waves for the S matrix. And unitarity is pretty simple to formulate in this language. It's that in the elastic strip where you don't have production processes, the S matrix is a phase, and beyond, as soon as other processes open, you have phase space to also produce these things. So you cannot be a phase anymore. You are smaller than a phase. It's straightforward to check. If you're given an amplitude, you just compute these integrals. You compute the phase, and you see if it works or not. It's straightforward to check, but it's hard to use to produce a good amplitude because you can invent your SJs, but they're never ever going to satisfy crossing symmetry. You can write, sorry, I didn't write the formula here to not clutter the slide, but you can write A as a sum of FJs. And if you just invent these guys to satisfy this, they're never going to satisfy crossing symmetry. So this is the thing that's really hard. That just makes this approach really hard. Okay, so that was it for partial wave unitarity. Now unitarity and the formulation we're going to use. Sorry, shall I stop moving or? Yeah, so the unitarity, so SS dagger equals 1. In terms of the amplitude, it's what I wrote before with small drawings. That's the elastic part. That's the inelastic part, and this T dagger T here has kind of an index contraction, and you have a sum over all the intermediate states, and also over the phase space, and here as well. So this square is not really a square; it's actually an integral over the on-shell phase space, right, of your cut. You have your two amplitudes T, and yeah, plus and minus refers to I epsilon stuff. So let's just. But you have this integral over the on-shell phase space, and with the delta function, just momentum conservation, and you end up that equation here, which looks simple when written like this, becomes this equation. And sorry, I forgot to say, this is true within the elastic strip. So where these guys are 0, you just remain with 2I in T222 equals T222 squared. And when you write this properly in terms of actual phase space variables and so on, you get that type of equation here. The S in front and stuff is just normalization factors. The P guy here is important, but it's just a Jacobian for the change of variable from this on-shell integral to this Z variable, which are just cosine of scattering angle. So I don't want you to be bored with the details. It's just that just to present a bit what this is about, because we're going to take another discontinuity of this in a minute. And I want you to stare at this equation. So yeah. Okay, yeah, I want to talk about this equation is true in the physical kinematics. And let me just do a quick intermezzo about 222 four-dimensional kinematics. So this plot where you don't see the green hashed regions, which correspond to the physical regime. So this is S here, and this is T. We have S plus T plus Q equal 4, M squared. And the physical kinematics of 1, 2 going to 3, 4, with these definitions for S, T, and U. The physical region is just defined by demanding that the cosine of the scattering angle is between -1 and 1. And that's enough to single out this wedge. And the wedge is S bigger than 4M squared, physical S, and T between 0 and 4M squared minus S, negative T in this range. So this equation here you derive in the physical regime. But it's quite, you see, this is the first source of problem. This is really hard. This is not crossing. You don't have crossing here. S and T are defining completely different spaces. So this is one first source of problem, and why you want to go to the next, why you want to take another discontinuity of this equation. I'm just trying to motivate this Mandelstam representation that I haven't introduced, but I'm going to come to why this equation of unitarity is not suitable, and you need something a bit more powerful. So we're in this physical regime. So it's not crossing friendly. Here you only have the discontinuity in S, and this is physical kinematics. So one way out, it's possibly not the only one, but one way out, and the only one that exists on the market, is to take another discontinuity of this equation in T, right? So at this point, you're not just doing optical theorem type things. You're really considering this equation as an equation between complex functions of S and T, and you look at the discontinuity in T, which is the difference between T plus I epsilon and T minus I epsilon in the physical regime. And then you can analytically continue this by a rather long process. I recommend Sasha, Miguel Carrera's, and Amit's paper on that, or Sasha's lecture notes that explain this Mandelstam equation very well. And this is how you come from this discontinuity of this unitarity to the Mandelstam equation. So what's in there? These are the key players. Rho is now the double disk in T, disk in S, or in S and in T, it's the same. So it's like a double cut of your amplitude. It's on the left-hand side. And on the right-hand side, well, you just take the disk of this guy. So now you have the T discontinuity in here. And eta and stuff, it's just another change of variable coming, but it's all coming from this original on-shell phase space integral between your states. And now that equation is defined for this row is gonna be defined in positive S, positive T quadrants, which is gonna be suitable for plane crossing. And this is almost the equation we want to solve. It just lacks the inelastic input, because if you remember, this is in the elastic channel. So we will want to solve this equation. We will want to look for functions such that their double disk is equal to the double integral of their single disk. Yeah.
On both sides, evaluating some double discontinuity, because that gives you a function that's defining like a whole region where you can go between different functions.
Yeah. You're losing information. Yes, if you have to take subtractions. So you're losing information for the rational piece, or any term that isn't. You also have single discontinuity, like pure log S terms, and these you also need to input. It's not just this double disk. There is more to the amplitude than the double disk. Also, we don't just solve that. We also solve with the single disk and subtraction terms. Yes. The only assumption is that you can do this continuity, this analytic continuation, and this requires that you have only the singularities dictated by unitarity in the S and T plane, which is an assumption. It's not proven. We can discuss it or come back to it in a few slides if you're not happy. Okay, so just quick thing. What do we do with rho? Because we want the amplitude, not the double disk. So with rho, we double integrate it to get to the amplitude. So what time is it? Just to be very. No, sorry, I don't have time for this. The simple case is that from the simple thing I wanted to say is that from the discontinuity of a function by applying Cauchy's theorem, you can reconstruct the function anywhere else in the complex plane, and you're just doing that twice because you know the double disk, so you do a double integral and you reconstruct the thing. That's of course for this you need that this rho function decays sufficiently fast and a bunch of other things, but then you get your amplitude by doing these double integrals, and this is the Mandelstam representation or a simple version of it. I'm not writing there's also a rho of S over S prime minus S type integral in there. Coming back to Emilio's comment. So and yeah, to be written down, it requires this notion of lightest particle maximal analyticity in that case, and that these things are converging sufficiently fast. So for the sketching of lightest states, scalar states, it looks like it's a good thing, but it's not proven. It's not a proven fact that QFTs would admit this representation in general. It's an extra assumption. It's a strong version of analyticity. So okay, yeah, that's the paper by Miguel and Amit and Sasha was mentioning. So this is the positive ST quadrant where we're now playing, not the physical region, it's another region. And the row function, the double disk, is going to be defined above these Landau curves. And schematically, the idea is that this is the only type of, so these Landau curves correspond to singularities of these graphs. These graphs, which you can think of as Feynman graphs. And you can see that just a single a box wouldn't have a double discontinuity, because once you've cut once, you get tree level on both sides, and you cannot cut the tree level. It's just a rational term. So you really need something that has a bit more structure in there, because now that you've cut once, you get two boxes, and you cut once again. So just like the discontinuity of the amplitude opens up at a threshold, the double disk opens up at these Landau curves. So it's 0 below, and it's non-zero after. And with this material, with this technology, people in the 60s, 70s went quite some way. This is in particular the type of things that Axe uses to prove this his theorem. And the thing that's really strong in that context is unitarity in the elastic strip here, because it's valid for all t and s in this range. And in the elastic strip, again, this part of the unitarity equation, or double disk unitarity equation, drops out, and you really have a fully non-perturbative equation about the amplitude. And in particular, the way to, it's a very quick version of Axe theorem. If you suppose that your amplitude doesn't have production processes, in particular, it doesn't have this guy here, right? It doesn't have this graph, because this graph corresponds to an intermediate 2 to 4 states. So it means that your double disk should start only not at this curve, but at this curve. And if the amplitude is non-zero, it needs to have some elasticity in here. But then by crossing, you have something which is non-zero here, which is 0 here, and you reach a contradiction, and the thing cannot work. So this is Axe theorem in 2 seconds. There's a bunch of other things that you can do with elastic unitarity, which are, some of them are in this hard to read book and hard to actually see on the screen. Right, so so yeah, this was just to set the stage and show you the object and kind of the context in which this guy is defined. Say that again. Complex, and that's the complex angular momentum book. Yeah, this was your question. Yeah, no, it's all about, yeah, it's the same type of things. It's how can you analytically continue in angular momentum. Yeah, this is all this whole program. So yeah, now I'll come to now that hopefully, so we have this Mandelstam equation, this row function, which is defined in this thing, and we want to play with this thing. This is the papers by Atkinson, who, by the way, is still alive, and very happy to see that his stuff can be implemented like 60 years after or something. First paper of the series is David Arkinson, so beware. Okay, so that I explained. Yeah. So that I explained. This is so that's, sorry. Now I'm going to explain how because his papers are mathematical proofs that there exist functions which satisfy these axioms, not like implementations or something. He just wanted to show that at least these axioms are not an empty set. And he succeeded. And he used that trick, that scattering from production trick. So how does this work? So his stuff is iterative. He wants to find a fixed point of a map. So this thing here is schematically the unitarity equation. It's the map you're trying to solve is phi of blob equals blob. And you see that if phi of blob you define as this right-hand side, indeed you're just solving that blob equals unitarity. Is that clear? Okay. So how do you solve f of x equals x? Well, the simplest thing to do, dates back from the Babylonians, to compute square roots in field and stuff. You apply the function iteratively, and hopefully you converge to the solution. It's this little staircase thing that we'll do in preschool. So now you want to think of the left-hand side of your unitarity as the function at step n+1, and you use the input from step n, which is just the function you're looking at, and this thing which you're not iterating. It's just the thing. It's constant. You're not touching it. It's a function that stays the same all along, and you're just cranking the wheel. And with not so much mathematical machinery, but quite some calculations, because you need to show that the map is contracting, which guarantees that you will converge to a fixed point. Sorry, that the map is continuous, which guarantees that there exists a fixed point, and then that the map is contracting, which tells you you will actually go to the fixed point. He can prove that these functions, this fixed point exists for some starting point and some input. And so yay, S matrices exist. Okay, so that I kind of mentioned, maybe not clearly at the beginning. I was saying that by treating the set of all these inelastic inputs, you're necessarily covering the set of the physical ones. So at least the set of physical F matrices is in there. Then the distance between these two boundaries is just an open question, I guess. But yeah, this philosophy is kind of geared towards Bootstrap because you're exploring that space of consistent object. And okay. Right, so I'll say a few things about the numerical implementation and show you some plots, and we can go to coffee. So yeah, this is laptop calculations. Just a bit cheating because it turns out Mathematica has a nice way to connect kernels by SSH. So you still kind of need at least 50 cores to do something in a reasonable time. So it's boosted laptop type calculations. We're still using Mathematica, but we hope to, like the next step is to do something a bit more fast, although frankly, the n-integrate of Mathematica, a bit tweaked, is kind of as fast as defo quad of Python. So, but it definitely can be improved by orders of magnitude. Yeah, so the plots I'll show you are not in the S&T, in this S&T positive quadrant. It's in the 1/s and 4/s and 4/t quadrants, which is the 0, 1 quadrant. And in that case, this curves, this purple and blue, which we don't see curves, map to these little straight lines here and there. And then this green thing goes to the green thing here. And rho is defined inside this double wedge area. So then you want to discretize because you want to evaluate the function at points, and this is how and then you interpolate. This is how you solve this equation, and you hope that when you take the size of the grid to 0, you converge to something that makes sense. So this type of grids are not good because you have a very poor resolution near infinity, which is near 0 in the 1/. variables. That's not good either. You just take the log, it's exponential. It's not good either because you have some weird spacing here, and it turns out you want to do some kind of meshing. The Mathematica has some package to do some, I don't know, some differential equation solving type of thing, finite element methods. And so you want to play with this kind of mesh. And that's the algorithm. in its simplest, I'm just repeating what I said with drawings before. In its simplest implementation, you start from a row 0. You compute in the unitarity equation. Okay, that I need to explain. If you want, the row 0 is the imaginary part of the imaginary part. In the unitarity equation, we had the double disk row equals integral of kind of modulus of the discontinuity squared. But that guy has a real part and an imaginary part. The imaginary part is just rho. It's the disk of the disk. But you start from row 0, so you need to compute this guy. You need to compute the real part of the single disk. So that's just a simple dispersion integral. And you get rho 1 by plugging in this full single discontinuity squared. And now I'm using T1, T2. Before it was Z prime, Z second, and also eta prime, eta second. Sorry for constant change of name. And then this function is the row elastic. You work that out only in the elastic strip S and for S. And you cross it to crossing symmetrize it. You add the inelastic input. You get rho 1. You iterate. Repeat it. Sorry, say that again. Oh, V. Sorry, yeah. I haven't. Sorry, V is pick your favorite. It's like it's what you will declare to be your input. I'm sorry, I forgot to say that. Yeah. So the input data are the starting point, which turns out to never matter. So we can set it to 0 and the V inel. So what you're doing is that you plug in, and then you iterate. So what you're doing is that you have your input data, V inelastic, and rho 0, which you can set to 0, at least for what we've seen so far. And that gives you a fixed point, rho infinity. This is how this business works. In 2D, you don't even have this double integral, so it's super easy. In 4D, it's really the bottleneck that you have to compute this double integral, and it's super costly, and there's no quick way to do it yet. Okay, and this is just coming back to Emilio's question. We don't just do the double disk, we also do the single disk row of S. And we actually also add a subtraction term, a constant, which allows the amplitude to go to a constant at infinity. And this is like the lambda coupling of your 5-4 theory. So the players of this game are you don't just get rho here on the whiteboard. Sorry, okay, you get actually lambda, which we treat as fixed. But you will get as an output your rho function and your row of ST function. But if you got the general idea, don't worry about what I said on the previous slide. Apart from the fact that it's important, we actually can play with a quartic coupling lambda, which is also an input of that game. So this is just to show some results, just some plots, and then I'll go to some more precise statements. So you start from this V inel function, which is defined in the inelastic regime, so quite far where near S and T go to 0, S and T go to infinity. In this example, it's something that has a divergence on an inelastic lambda curve, another one, but it could be just a finite blob. It generates for you some rho, and some rho of ST, some rho of S, and then you can check unitarity, and this is the interesting part of the thing, which I'm coming to. So without subtractions, actually, it was really hard. It didn't quite work, actually. Without subtractions, it's really hard to find a way to converge it. Either the grid convergence is very slow, or it's that you need to do better than just interpolating between points, and I add some actual analytic input. With subtractions, it works extremely well. The coupling lambda is what really drives the iteration. And so that's a plot of the convergence. It's in log scales. It's the difference between two successive rows of whatever variable. and it's called linear convergence, when it's linear like that in log scale. The Newton method, which is another one, has quadratic convergence, so it would be like even faster. But this means that this exponential convergence is called linear convergence. It means you're going somewhere to the fixed point. So the amplitudes have the correct Landau curves, of course, by definition, because this is the thing you really it's built in. And now one game we could play is now that you have this thing, you have your V inel, your lambda, you can ask how small can the inelasticity be? You know, it's not supposed to be 0, but how small can it be? How small is it? So the thing we tried is to just set it to 0 to see if you get something. You keep your lambda, but you set the thing to 0. And so it produces some kind of a 5-4 theory. So that's somehow the iteration you're doing. You're gluing these things with two particle intermediate states. And when you set the V inel to 0, which is called sigma here for some reason, this is the equation you have. And in particular, that recursion will never produce a graph where all the cuts are 4 particle cuts, like this box here. See, however you cut this box, you have 4 particle intermediate states. And this just glues 2 by 2, so you will not produce this graph. So it's not exactly 5-4, because 5-4 has this graph, as Feynman rules tell you. And this graph, note that it has order lambda to the 4th, because it has 4 vertices. Yep, I want to skip this. So this is results for this theory, which iterates like that. Yes, so I mentioned the linear convergence. The S0 wave converges to a pure phase, which is built in, but sorry, S0 wave is the Sj with j equals 0 partial wave. Yeah.
So you want to diagnose how small an inelastic scattering is, and then you try to set it to 0, and then how far away is I guess what's quantitative, right? And just take some of the graph.
Yeah.
How does it diagnose how small the inelastic scattering is?
Yeah. Okay. So there's several aspects to that question. Because you could think that because V inel is not exactly the inelastic amplitude, it's your input, but then the amplitude builds up on top of that, iterates, and creates also some row inelastic part of the amplitude. It's not like you glue something elastic to your V inel. The amplitude is a continuous thing, and it will generically be bigger than. So if you started from, just do a one-dimensional example. If you started from some V inel, which is like this, and then 0 in the elastic, the amplitude, the type of functions you would get would do something like this. So indeed, in this inelastic range, you don't just have the inel. So you could think that maybe if you actually do something that the inel that goes a bit negative, you might be able to decrease even more the inelasticity. That's correct. And this is on the to-do list. It's just kind of a motivation for why one could try to set V inel to 0. It's like the simplest thing to do, but you could do something wiser. Does this answer a bit your question? Okay, thanks. Okay, so the S0 wave is just set to 0 almost by the equations themselves. I mean, sorry, not almost. It's exactly set to 0 by the equations themselves. I don't have time to explain you why, but I can explain you afterwards. The other S waves are not set to 0. It's only S0, which is constrained to 0. And so you're expecting to see no inelasticity in there. And indeed, it's very clear that it converges to just pure phase. And it's also very clear and very nice that the other waves, S2, S4, and so on, converge to something which displays very clearly and in a very clear converged way, accurately, numerically accurate way, some inelasticity. So this would be for different couplings from -π/2 to 3π. Sorry, I forgot to say one important thing. The range of couplings in which we converge is between -π and 5.5π. I'll come back to this at the end. It turned out that this is a small portion of the range of couplings that PPT-VRV derived. So, so although we are more accurate for inelasticity, we describe possibly fewer S matrices. And this is one source of things to improve. I'll come back to this at the end. So yeah, this is a plot of these various S2 waves corresponding to various amplitudes with various couplings. And you can see this bump here below 1. It's very small, but it's very clear numerically. And you can also see that it doesn't converge to 1 at infinity. And this could be some source of, some reason why these other algorithms are slow, is because they kind of impose elasticity as S waves smaller than 1. So any solver tries to drive all these quantities to 1. And this could be a reason why this is slow and doesn't converge. And yes, this next slide is just to show that, it's just to say that the property of this inelasticity are just not just random, they also satisfy some stuff you can derive from analytically. That's also in that paper by Sash and friends. And we have some good numerical evidence of this. When we increase the size of the grid, these points where the color is hard to distinguish seem to want to lie more and more along this curve, and this curve, black curve here, is the equivalent of this red curve there. So the inelasticity we get, in short, seems to be the correct type of inelasticity. This is some recent paper that Yutin mentioned yesterday, that if we look just at the red curve, which is d = 4, describes some observables tau10 and tau11, which are derivatives of the partial waves, and they're supposed to lie inside the red region. And our curves, our points, our data points for this inel = 0 theory lie exactly at this, seem to lie precisely at this boundary. So they seem to relate to some kind of extremal S matrices, because they would be on this boundary. But by the way, this boundary is, this guy's also figured out that this is just one loop 5-4 theory. So although this is like super heavy duty numerics, in the end you get this stuff, which is the 5-4 theory, one loop 5-4. But yeah, again, with their method, they cannot probe precisely X physics. And the interesting thing is that our S matrices at this boundary for the VNL = 0 theory seem to display a clear, tiny, but clear unitarity violation, size 10 to the -10 in the S2 wave. And this is interesting. So these several curves are again for several couplings. And you can ask, okay, how large is this little unitarity violation here? It's a violation because it's above 1, right? It's a violation. How large is it? And you plot this against the coupling, and it's a clear λ⁴ violation. And λ⁴, if you remember well, it's a graph that cannot be produced by this thing. So it's not a good. So what this says is that you cannot set this inelastic guy to 0. It will produce some violation. So to actually accurately answer how small the inelasticity can be, you need to play with this. You need to find inelasticity that corrects this bump, and then you can maybe see how small can it be. And this is a work in progress. I'll just conclude in 2 slides or something. To improve, the best thing next thing to improve would be to implement some gradient descent on this problem. In 2D, we could do some Newton method, which is called Newton-Raphson somehow by numericists, and that converges much faster because the Newton method, if you remember, is helped by a gradient. You take the derivative, you follow that thing, and you don't just go down the staircase. You actually follow the gradient, and it converges extremely fast. You have to pay the price by computing a gradient, and this is where all the modern machine learning thing is useful, because with this idea of what they call back propagation, by computing the thing, you also compute the gradient, and you don't have to compute it again. So it's fast. It's very fast. But for this, you need to get rid of that double integral and turn that double integral into a kind of matrix multiplication. And this is the thing that is hard to that needs to be done next if we to improve the numerics in this way. Okay, so perspectives. I just mentioned that. Also, yeah, then you'd be able to run this thing on GPUs and be extremely faster. The perspective is so the next thing to do is to, well, understand this how small can inelasticity be in this context. Improve the numerics. This is extremely easy to generalize in other dimensions. So 3D or 3.5 or whatever is very or 5 or it's just the code is nothing is to be changed in the Mathematica program almost. The things that you would want, the physical results you would want to obtain are amplitudes that saturate the Froissart bound, because they would be kind of maximal in some other sense. To obtain a good fit for a pi on S matrix. So what I mean by this is you input data. You want to get the pi on S matrix. You would need to know what is this V inel that you need to input. And to know it, you could input data from chiral perturbation theory, from lattice, from a variety of sources, and you might then get a good fit, a good function that would be a good fit for a pi on S matrix. It would be a fit, not a derivation. And then coming back to Sabrina's question at the beginning, you want to do this for gravity. This is the ultimate goal. You want to try to do this for gravity, but then of course things are hard in 4 dimensions. You have infrared divergences. You don't really know what states to sum over in the unitarity and so on. It would be great to see how this iteration unitarizes gravitational amplitude. Do you see black hole? Do you see strings? I don't know. Yeah, so this is the only place where the word celestial appears. Could the celestial program eventually? It would be great if the celestial program would give tools to reformulate these equations maybe in a simpler way, or yeah, I don't know. And is there celestial scattering from projection? I don't know. Okay, I'll stop here. Thanks for your. Oh no! Sorry. I want to advertise. So I moved to Annecy last year. It's a small town, just a drive away from CERN. We have a pretty lab in winter and a nice lake in summer. And I'll be hiring 1 postdoc. So if you know someone who wants to work on this type of things, or if you want to come to just visit us, come over. It's friendly and beautiful, and we're close from CERN. And George knows the place is nice because he's been there often. So thanks for your attention.
Save about like the loop order, it wouldn't be the same that they're for like what your external space would be. I think
Yeah, it probably wouldn't be exactly. Yeah.
Second question. Okay, so are you trying to rule out your modified biforce theory?
Yeah.
Like, you don't want to become some kind of
Yeah. It cannot work. Yeah.
Wait, why can't it? What's the reason why?
Because it does produce this this unitarity violation.
Okay,
It's very small, but it's okay. It really seems to be there. You change the grid, it doesn't change. It's just there. Yeah.
Okay, and the third question is, I thought that from the iteration of the map, like you were building a unitarity at least at the level of like the 6 point of the map should be that it's the unitary equation where it's like 1 times the.
Sorry. Right. Sorry, I forgot. Sorry. The only thing that Atkinson gives you is something that satisfies elastic unitarity. Then you need to check inelastic unitarity. So in these curves, that's again this S2 wave violation of unitarity. You know that. Yeah, actually, you don't see really it nicely here. Yeah, on this curve, you see that there is some numerical glitch because anything below the elastic unitarity starts at around here, and this should be a phase. So you see that there is some numerical glitch probably created by this bump. It could be both, but the thing that's most likely and the most easy to investigate is that V is a bad starting point. The starting point for the V is a bad object. The starting point in 2D actually we had some interesting stuff on the starting point, but using Newton method with the fixed point, the starting point never matters. When you're driven by the gradient, you can actually reach different type of solutions, and in 2D you reach solutions with more CDD, what's called CDD zeros or CDD poles or S matrix, integrable S matrices, and then it depends on the starting point. No. Well, first off, these amplitude would be gravity, so we don't really have anything to say about them. Now, if someone hands you an amplitude, it's very easy to see if it's good or bad. You just compute the partial wave unitarity and you see if it satisfies wherever that was, if it satisfies this. If it's one everywhere, it's a problem. If it's this and it's crossing symmetric, you have a good object. This is weaker. And our stuff demands a Mendelssohn representation and so on, but this is the only way that gives you crossing symmetry and analyticity. Oh, sorry, no. You would also want to check that it has the correct Landau curves, because this is also non-perturbative statements. Yeah.
I actually have a very naive numerics question. So for your numerics, the violation to unitarity is 10 to the minus 10. How are you certain that that's not a product of numerics?
Yeah, it's 10 to the minus 10 because when you compute the S2 wave, when you compute SJ waves, you have some normalization factors that end up damping stuff, but it's not as small as 10 to the minus 2 as before you normalize it. So it's something that's bigger than your noise. Also, you take the grid size, you increase the grid size, you see the thing moves. But yeah, it's a great question, yeah, of course.
Any other questions? Okay, if not, let's thank the speaker again.
Thanks.